Hello friends, welcome to our channel RedsInfoHub. I am Mr. Reddappa Tanneeru. In this video, we will discuss a new chapter, moving charges and magnetism. Moving charges and magnetism. And in this entire chapter, we will discuss about two very important points. Number one is calculation of magnetic field, and number two is calculation of magnetic force. And for calculation of magnetic field, we use two tools, very important tools. One is Biot-Savart's law and another one is Ampere's law, right? And after discussing some applications of this, we will discuss about how to find the magnetic force on different elements like current carrying conductor and moving charges, etc. And in addition to this, we will discuss few more points. Few more points. We will see those what are those in due course. First, we will start with what is Biot-Savart's law. That is how to find the magnetic field. How we use Biot-Savart's law. Before entering into or starting with Biot-Savart's law, let us discuss few prerequisites. Especially, we'll see what are the sources of magnetic field. Sources of magnetic field B. In your lower classes, we have studied that a bar magnet produces magnetic field. Right? Bar magnet looks like this. A bar with the north and south poles, and we know that magnetic field lines starts from north pole and ends at south pole outside, and they travel from north to south outside, and inside they travel from south to north. So they will form closed loops like this. They forms closed loops like this. Unlike electric field lines does not form closed loops, but magnetic field lines forms closed loops. That is one point. So from this we have tried to recollecting that bar magnet is one of the sources of magnetic field. The another one is current carrying conductor. Current carrying conductor. The first person who has observed this is Ørsted. Ørsted is the first person who has observed that a current carrying conductor, if you have a conductor in which if current I is flowing, it produces magnetic field. And the direction of this magnetic field was observed by using right hand thumb rule. If you stretch the thumb of right hand in the direction of a conductor, the direction of curling fingers, twine, like twine. This direction of curling fingers will give you direction of magnetic field lines. This is so. Current carrying conductor is another source of magnetic field. This was first observed by Ørsted, right? And the third source of magnetic field is moving charges. Moving charges. So if you have a charge Q and if it is moving with the speed V, this also produces magnetic field. So these are the three sources of magnetic field. Right? About this, we are going to discuss more clearly with few special cases in the due course in the coming videos. Now let us discuss about this point. How to understand how to calculate magnetic field produced by current carrying conductor. Ørsted has observed that current carrying conductor produces magnetic field, but how much field it produces? To understand that, two scientists, Biot and Savart, has formulated a law. It is an experimental law, you can say, and this law is called Biot-Savart's law. For calculation of magnetic field producing by current carrying conductor, as already we have discussed, we can use Biot-Savart's law or Ampere's law. First we will see Biot-Savart's law. How to calculate the amount of magnetic field and the direction of magnetic field also by using Biot-Savart's law. Right? Let us start with Biot-Savart's law. Yes, let us see what is Biot-Savart's law. But before discussing about Biot-Savart's law, let me give you few points about magnetic field. Magnetic field is measured by an SI unit called Tesla or Weber per meter square. SI unit of magnetic field is Tesla Tesla, it is denoted by capital T, Tesla. This can also be called as Weber per meter square. Per meter square, it is denoted by WB per meter square. WB some space meter square, meter per minus 2. This is the SI unit of magnetic field. Whereas the CGS unit of magnetic field, CGS unit of magnetic field is Gauss, Gauss. There is no symbol for Gauss. Tesla is denoted by capital T, whereas Gauss you have to write as Gauss only. There is no symbol for that. As the CGS unit usually will be a smaller unit. 1 Tesla we can say is equal to 10 to the power 4 Gauss. If you, while doing numericals, you have to remember this conversion relation. If the value of magnetic field is given in Gauss, then you have to write 1 Gauss is equal to 1 by 10 to the power 4 or 10 to the power minus 4 Tesla. Remember this conversion relation. Obviously, magnetic field B is a vector quantity. Whether it is magnetic field or electric field or a gravitational field, any field, usually the fields will be vector quantities. That means it will possess both magnitude and direction. Now, to understand the magnitude of magnetic field, we use here Biot-Savart's law. How to calculate the amount of magnetic field or magnitude of magnetic field produced by a current carrying conductor especially. So let us see what is Biot-Savart's law. So you can take down subheading Biot-Savart's law. Two scientists, Biot and Savart. Here you can observe Biot-Savart's law. But in this T is silent. We have to read or you have to pronounce it as Bio. T is silent. Biot-Savart's law. This guys has formulated the law which says that if you have a current carrying conductor, due to this, if you want to find the magnetic field at a point P which is at a distance R, you have to divide this into small elements. So one such small element, let us consider it as dl. To find out the small amount of magnetic field due to this and likewise due to all elements and add them, we'll get the total field due to this conductor. Let us call this conductor as xy. So for adding, we can use summation or integration. In this case, in our case, we use integration while doing the numericals, right? First, according to Biot-Savart's law, this small amount of field produced by the small element dl is observed to be let us see here, dB is observed to be directly proportional to I, current flowing through this element, and also directly proportional to length of the element. And it is also observed that dB is directly proportional to sine of theta. This theta is angle between the line joining the point and the element and the direction of current. This is theta. Is it clear? And is also observed that dB is proportional to 1 by r square, or it is inversely proportional to square of the distance between the point and the element. By combining all these, we can write this as dB proportional to I dl sine theta by r square. And in physics, especially whenever you come across these equations, when you are writing an equation, means you have to equate it. Instead of proportionality, if you write equal to symbol, we have to replace this proportionality with a constant. We call as proportionality constant k into I dl sine theta by r square. In this case, this proportionality constant is represented as mu naught by 4 pi into I dl sine theta by r square. Are you following? Here mu naught by 4 pi is what? Proportionality constant, and this gives the what? Biot-Savart's law, and this expression gives the magnitude of the amount of magnetic field produced here at a point P which is at a distance R due to this element, small element of length dl. Is it clear? And this gives only magnitude. We know magnetic field is a vector quantity, so you have to know what is the direction of a field also. Before discussing about this, let us see a few more points here. Here in this case, the proportionality constant mu naught by 4 pi, where mu naught by 4 pi is equal to 10 to the power minus 7. units. What is the unit of this? This is equal to, if you write dB into r square by IDL sin theta, if you write, you will get the unit. That unit is Tesla meter per ampere is the unit of mu naught by 4 pi. Where again mu naught, where this mu naught is can be expressed as 4 pi into 10 to the power minus 7. 4 pi into 10 to the power minus 7 Tesla meter per ampere. This has given a special name called permeability of free space. What is that? Permeability of free space. I hope you guys have copied this, or if not, just take a screenshot, then I will go ahead with the remaining part. Take a screenshot, copy it down, where mu naught is called what? Permeability of free space, Is it clear? Mu naught in this expression is permeability of free space, and its value is 4 pi into 10 to the power minus 7 Tesla meter per ampere. While doing numericals, you have to remember these values. Is very, very important. Usually in numericals they will not provide the value of this sometimes, so you should remember this. Okay, right? So this is this expression gives what? Magnitude of the field calculated by what? Biot-Savart's law. We also call it as scalar form of Biot-Savart's law. Then to understand vector direction of this magnetic field, we have to write the what is that Biot-Savart's law in vector form. Let us see what is that vector form. The vector form of Biot-Savart's law explains you the direction of magnetic field produced by current carrying conductor. So if you observe in this, it is IDL sin theta. Here it is whenever you observe some sin theta form in an expression in the product relation, scalar and vector product relation, you have to think that it can be expressed in cross product form. So by keeping that in mind, you can rewrite this as dB bar is equal to mu naught by 4 pi into I dl bar cross r cap by r square. So this is the vector form of which law? Biot-Savart's law. Is it clear? Here r cap is the unit vector in the direction of this, or unit vector of position vector of this point from the element. Unit vector of position vector of this point from the element. Is it clear? So if you draw a line with an arrow, this gives position vector r bar. So unit vector of that is given by r cap is equal to the vector by its magnitude. Because of this, or by using this, we can also express this as dB bar is equal to mu naught by 4 pi into I into dl bar cross r cap. If you replace with that r bar by r, this r square into r becomes r cube. Are you following? R bar by r square into r becomes r cube. This is another way of expressing vector form. In case in r cap form or in r bar form, in either of this you can express. While doing with MCQs or objective questions, any of this you may get. So you have to have an idea about both of these expressions. Is it clear? This is called the vector form of Biot-Savart's law. Right? Yes. Now let us try to understand how to represent or how to understand the direction of that magnetic field from the vector form of Biot-Savart's law. Vector form of Biot-Savart's law is dB bar is equal to mu naught by 4 pi into I into dl bar cross r cap by r square, or dl bar cross r bar by r cube. Right. From this you have, if you recollect the concept of vectors from the 11th standard, it is a vector form dB bar equal to dl bar cross r cap by keeping all these constants. It is something like cross product c bar equal to a bar cross b bar. So the resultant will be in a direction perpendicular to both dl bar and r cap, right? So in that way, if you want to understand, you can use the right hand thumb rule. What this right hand thumb rule tells is, let me explain you. If you have a current carrying conductor, something like this, by using right hand thumb rule, if you stretch the thumb of your right hand in the direction of current, and if you want to find the field at a point P due to this current carrying conductor which is at a distance R, then if you stretch the thumb of your right hand in the direction of current and curl the fingers, so that if you curl the fingers at this point, in what direction the fingers are curling, like if you curl at this point, if you observe, the fingers are going into the plane, right? So at this point the direction of magnetic field is given as B bar. It is into the plane. Is that clear? According to right hand thumb rule, if you stretch the thumb of your right hand in the direction of current and if you curl the fingers, then the direction of curling fingers at that point gives the direction of magnetic field. Right? Next, right hand palm rule. What is this right hand palm rule tells is, if you have a current carrying conductor I, at same way at a point P, if you want to find the magnetic field which is at a distance R, then right hand palm rule tells is, if you stretch the thumb of right hand in the direction of current and then if you stretch the fingers of right hand onto the point, just stretch, no curling, stretch the fingers onto the point, and then the direction of the palm gives direction of field. Here, what is the direction of palm? Palm is here, it is facing the board, so this is the direction of palm, so it is into the plane of the board B bar. Whereas if the current direction is this, you can say with an example, you can say is an example. Whereas in this case, if the current is flowing down at the same point P now, which is at a distance R, if you want to understand the direction of magnetic field, you have to stretch what? The thumb in the direction of current, like this, of the right hand. Then stretch the fingers onto the point, just stretch, no curling, stretch. Then the direction of palm gives direction of current. Here the palm is not here, this is the palm, right? So the direction of palm gives the direction of current. It is outward. Outward is represented by a dot symbol, so this is dot B bar. This is outward, where a cross represents inward. You have to remember here onwards the direction of directions, how to represent, not only for magnetic field, for current, force, for any vector, you can use these notations, cross and dot, to represent into the plane and out of the plane. Okay, fine. Whereas from another example, if you have a current carrying conductor, the conductor is such that the current is flowing into the plane, so that current direction is into the plane. Then at a point P, which is at a distance R, what is the direction of magnetic field? By right hand palm rule, if you stretch the thumb in the direction of current and stretch fingers onto the point, direction of palm is downward. That gives the direction of magnetic field. Is it clear? This is the direction of magnetic field. Another example, if you take, see, if you have a conductor such that in which the current is flowing out of the plane, stretch the thumb in the direction of what? What is this? This is the current, and at this point P, which is at a distance R, if you want the field, stretch the fingers onto the point, just stretch, right? No curling. Then the direction of palm gives the direction of magnetic field. Palm is upward, so here the field direction is upward. Now, did you understand? So by using these examples, you can do the example. While doing the examples, you can make use of these points. Is it clear? Let's take care, and in the next session or next video, we will discuss about the continuation of this. Let's take care, everyone. Yes, guys, take care. Bye bye.